Greetings, math people, and welcome to lesson 3 of differential equations. In this particular video, we will be solving first order separable differential equations. Let's get right into it.
First you separate and then you integrate. Just follow these steps and you will do great. First you separate and then you integrate. Just follow these steps and you will do great. First you separate and then you integrate. Just follow these steps and you will do great.
Here's the season to be serving.
When I was solving equations, I was feeling amazing.
All right, so the first thing I would like to do is to outline the anatomy of a differential, of a first order separable differential equation. Now, in the first lesson of this differential equation series, we solved differential equations where the differential equation was simply a function of x, and it was solved by mere integration. And integration will always be the key component to solving differential equations. It's just separable differential equations will have a little some algebraic manipulations before and after the integration to give a complete solution. So for a differential equation to be separable, it should be the product of two functions, a function of x and a function of y. So we say that a separable differential equation is of the form where dy by dx equals f of x times g of y. So it's a product of two functions, a function of x and a function of y. We call it separable because algebraically we're able to separate these functions since they're being multiplied by simple division. And where if I divide, I can rewrite this as dy over g of y, and that'll be equal to f of x times d of x. And it's very neat the way the Leibniz notation really works smoothly with solving and manipulating differential equations. Now, in this particular form, so in this form of a separable differential equation, f of x could be a constant, g of y could be a constant. It could be 1 actually. So we would also consider a separable differential equation in first order because it's the first derivative, but we can also consider differential equations of the form dy by dx equals just f of x, which is what we did in the first video, and also dy by dx equals just g of y. So those forms are also considered separable differential equations. And really the second one more because this one really has to be separated. The first one, although we can think of it as a separable differential equation, it's really, as we saw in lesson 1, just solved by mere integration. But anyway, so the way we solve a separable differential equation is we separate. So first we separate and then we integrate. So when I have dy with a function of y and dx with a function of x, at that point I can just integrate both sides and solve for y. And so that's why the song says, first you separate and then you integrate. Now for my AP Calculus students, when taking the AP exam, you have to show the separation or you'll get 0 points on your differential equation free response question. So you have to show, even though some of this, the separation and even the following integration, subsequent integration, you can do in your head if you're taking the AP Calculus exam and the class as well. You need to show the separation. That's a stickler that they have on that. Now, if you're Cal 2 student in college, your professor may let you slide, understanding that he knows that you understand you're going to separate and integrate, and a lot of that can be done mentally. All right, so let's just go ahead and work out some examples of some separable differential equations. First order separable differential equations. All right, so this is my first example, and this is the first order separable differential equation. This function here is a function of g, which is, a function of y, which is y plus 1, and a function of x, which is 1 over x, if you will. So you may say this is a quotient, not a product, and quite honestly, a first order separable differential equation, if I want, I can write it as f of x over g of y, because any product can be expressed as a quotient, and any quotient can be expressed as a product. So that's no big deal. But I can just consider this 1 over x to technically think of it as a product. So the first thing we'll do, of course, is we'll separate. And so what the separation means is we're going to bring the y function over with dy and move dx over with x. And so what we'll do is divide by y plus 1 and multiply by dx. And what we'll get is dy over y plus 1 equals dx over x. So that's the first step, to separate. And then the second step is to integrate. So now we're going to integrate. And dy over y plus 1 is ln y plus 1. And dx over x is ln x plus some constant. Of course, when we integrate, there's a constant here and a constant there. And so say I have C1 on this side and C2 on this side, and say I subtract C1 from both sides, this is going to give me another constant. So we customarily just put one constant on one side, and I like to put the constant on the right side. So now we have to just solve the equation, an explicit equation with y equals in terms of x. So we want to find an explicit function of y in terms of x. So there's a little algebra involved. And so what we'll do is we'll make these exponents of e, and e ln y plus 1 will just give us y plus 1. And e ln x is just x. And this will be e to the x times e to the power of c, if you understand the properties of exponents. But e to the power of c is just another constant. So that's just going to be c, again, times x. So that's cx. And then to solve for y would be cx minus 1. So that's actually the solution to that differential equation. Not in this particular video, and we did something in the first video where there was an initial condition, and we can utilize that initial condition, to find out the exact value of c. In this particular lesson, there won't be any initial condition problems, so everything will be left with respect to c. All right, let's go ahead and try another problem. So this differential equation is dr d theta equals r squared plus r over theta. So again, we're going to separate. I'm going to bring the r function over with r and d theta over with theta. And so what we'll get is dr over r squared plus r equals d theta over theta. So first we separate, then we integrate. Now, this integral right here may seem a little bit difficult. It's just going to require partial fractions. At least that's the way I would like to do it. So I'm going to just concentrate on this particular guy for a little bit. And I'm going to say that 1 over r squared plus r. And if I factor r squared plus r, that's r times r plus 1. So I'm going to say that equals a over r plus b over r plus 1. And, if you've never seen partial fractions, I'm going to choose convenient values for r to solve for a and b. And so first what I'll do is I'll multiply everything by r squared plus r, or r times r plus 1. And when I do so, it will cancel everything out here and just leave me with 1. I'll write it right here. And here the r would cancel, and it would be a times r plus 1. And here the r plus 1 would cancel, and it would just leave me with b times r. And so this is what I mean by choosing convenient values for r to solve for a and b. So for instance, if I make r equals 0, so r equals 0 implies this would cancel, and this would be 0 plus 1 times a equals 1, so that implies that a equals 1. And if I let r equal -1, so r equals -1 implies this would make this 0, will cancel out that a, and that'll be, give me that b times -1 equals 1, so that implies that b equals -1. So therefore, I can write 1 over r squared plus r as 1 over r minus 1 over r plus 1. And so these are things I can easily integrate. So, looking at this integration, dr over r squared plus r seems pretty difficult, but if I rewrite this, this is just an equivalent expression as, the integral of dr over r minus dr over r plus 1, I can easily integrate. So let me transfer that to a new page. And so I'm going to rewrite this integral dr over r squared plus r as dr over r minus dr over r plus 1. And that's going to equal to d theta over theta. And I'm going to integrate all that junk. So let me write what I was referring to. So again, this is going to be this. So this is going to be the integral of dr over r. This is the integral of dr over r minus the integral of dr over r plus 1. And that's going to equal d theta over theta. And I'm integrating that as well. All right, so this is ln r minus ln r plus 1 equals ln theta plus some constant. All right, so and the additional work on these separable differential equations compared to differential equations we did in lesson 1 is yet, after we integrate, it's not over. We have to do some algebraic manipulations in order to get it to an explicit function. So by the properties of logarithms, I can make this these two logarithms one logarithm, and this would be ln of r over r plus 1. And that, of course, equals ln theta plus c. And if I make these both exponents of e, this will leave me with r over r plus 1 equals, again, now e ln theta is just theta, and that's times e to the power c, which is just c. So this is going to equal c theta. All right, so still more algebra to solve for this. So let me write this on a separate sheet and do the algebra to solve for r. So what we have is r over r plus 1 equals c theta. So I can multiply both sides by r plus 1 to get rid of my denominator, and that would give me that r equals r c theta plus c theta. So, r times c theta is r c theta, and 1 times c theta is just c theta. And bring everything with an r to one side. So r minus r c theta equals c theta. And if you factor out an r, you'll be left with 1 minus c theta, and then divide by that. So r would be c theta over 1 minus c theta. All right, that solves that particular differential equation. Let's go to the next one. So the last two I'm going to do, they represent problems that are indeed first order separable differential equations, but may not look the part at first sight. All right, so this guy. So again, initially this may not look like a product of two functions, because it looks like just one function. But if we understand the properties of exponents, then we understand that e to the power of x plus y it's the same thing as e to the power of x times e to the power of y. So we do have a product of functions. And so if I separate, I'll get dy over e to the y equals e to the x dx. And dy over e to the y may be better to think of as e to the power of negative y dy equals e to the x dx. So first we separate, then we integrate. So when we integrate this puppy, the integral of e to the negative dy, I think I write it over here, would be negative e to the negative y. And of course, the integral of e to the x is simply e to the x plus some constant. So now, once again, it's time to do our little algebra. So this negative e to the negative y, I can write that as negative 1 over e to the y equals e to the x plus some constant. And what I can do is basically make these switch places where it's negative 1 over e to the x plus c equals e to the y. I don't think I have the room to write that here, so I'm gonna write that on a separate sheet. So again, what I'm gonna do is I'm gonna move this e to the x plus c here, and then the e to the y over there. And so what we're left with, we'll be left with that e to the y. So e to the y equals negative 1 over e to the x plus c. And now we can take the natural log of this stuff. Prior to taking the natural log, let me change this sign and make that a positive 1 and make that a negative x, a negative e to the x and a minus c. All right, so now I want to take the natural log of both sides. So the natural log of e to the y is simply y. The natural log of ln 1 over negative e to the x minus c. Again, before we had two logarithms that were being subtracted and we condensed them to one via division. Well, here we have one logarithm with division. We can expand it to two logarithms with subtraction. So this is the same as ln 1 minus ln negative e to the x minus c. And of course, ln 1 is 0. So y is negative ln negative e to the x minus c. All right, there's that one. And we will look at one last first order separable differential equation. And again, these last two, they don't look separable at first, but a little manipulation will get them there. All right, so the last one is this guy, and you may look at this and say, that's not separable, but just a little factoring by grouping, you will show that this is indeed a product of two functions, and it is indeed a separable differential equation. And so if you just look at these first two terms, what's common to both of them is y, so I can factor out a y, and it's y times x plus 4. And if you look at these last two terms, I can factor out a 3, and it's 3 times x plus 4. And so these are common factors. So factoring by grouping would make this y plus 3 times x plus 4. That's, of course, dy by dx. And so there we can easily separate, and it will be dy over y plus 3 equals x plus 4 dx. And first we separate, and then we integrate. Just follow these steps and you will do great. So the integral of dy over y plus 3 is ln y plus 3. I'm going to try to fit this in. Ln y plus 3. And the integral of x plus 4 is x squared over 2 plus 4x plus some constant. We'll make these the exponents for e. And e to the power of ln 3, e to the power of ln y plus 3 is just y plus 3. So y, I'm going to subtract the 3. Now e to the power of all this is just e to the power of all this. But e to the power of c, again, is a constant. So that's going to be c times e to the power of x squared over 2 plus 4x. And remember this 3 that was there minus 3. All right, so that's going to conclude our third lesson on differential equations. Again, the theme here was first order separable differential equations. And this is something that you'll cover in your ODE class and also in your calculus class. These type of differential equations are covered. So whether you're a student taking calculus right now or a student about to take differential equations, this lesson should be useful for both of you. And we will see you next time.
First you separate, and then you integrate. Just follow these steps, and you will do great. First you separate, and then you integrate. Just follow these steps, and you will do great. First you separate, and then you integrate. Just follow these steps, and you will do great.
Tis the season to be serving.
When I was solving equations, I was feeling amazing. Problem after problem until the day's end. Solving, keep solving, and turn the page in, and still keep grinding. Solutions keep finding. I have never seen a problem like this, but I know exactly where it fits. First order, separable ODEs. Now I know what to do, holy me. First you separate, and then you integrate. Just follow these steps, and you will do great. First you separate, and then you integrate. Just follow these steps, and you will do great. First you separate, and then you integrate. Just follow these steps, and you will do great.
Kind of a mathematical outlaw, a kind of a mathematical gangster.